Sorry about that, guys. Okay, so anyway, with the bee gone, with the bug gone, if you get okay, no, lame joke. Anyways, so yeah, the first solution that comes to my mind is we can. So there are 26 alphabets, right? I think that is definitely always a given, and we're definitely dealing with the English language. Um, if there are 26 alphabets, we can have a Boolean array which will store whether a specific character has been replaced yet or not. So, um, so as we proceed with the characters in string s, or we can actually have a Boolean hash map, uh, which basically stores all the Boolean objects, or yeah, a Boolean hash map with integer keys, so that every time we access a key, we can see if that specific key, which corresponds to the indice index of the array in S, has already been replaced. So let's say we traverse through S. My plan is if we replace G, then we're also replacing the G's in the other instances of S, right? But we still have to keep going until we reach the end of S. So how do we know that once we reach the second indice, which is the last G letter, that we have already replaced G yet in this array? Simple. We check the hash map instance after updating G once, and we check if is replaced in that hash map indice is true. So so we can have a hash map with 26 letters, and if G in the 26 indexed hash map indicates true, that means G has already been replaced. So we don't do anything with that. We just move on all the way until the end, and that way we'll be able to accomplish it in ON time, but O26 space, which is not that much space, right? Because you can have like really long strings, but it won't change the fact that you only need 26 lettered hash map with O1 access time, so you don't need to repeat 26 iterations, which is why it's not a hash map, not an array. And we can definitely check whether a certain character has been replaced. If it has not been replaced yet, then we replace it, and at the end we check if the new instance of s equals t. If it is not, we return false. If it is, we return true. So that is one way of doing it. So that solution specifically will have ON time complexity. Yeah, definitely, because we will need to traverse through every single character inside S, and I think that cannot be improved. Let's think of another solution. And it will have O26 space, which is basically constant space, so it's all good. Okay, so let's look at another solution. Linear time in OS01 space. That's what we have so far. So we know that the Java's replace method, it replaces every single character inside the string. So the other thing that we might be able to do is we can get the unique instances of the letters in the string. So what we're doing is last time we were just iterating through the entire string. Yeah, exactly. And this time what we're doing is we are taking each and every character, counting the number of unique instances and replacing them and them only. Okay, cool. So the other solution could be we traverse through the string to get the unique instances of each character repetition. So yeah, so we can have instead of having a Boolean hash map, we can, or we can have an array which a 26 is 26 a 25 indexed array which holds the counts of each of the letters, right? So we can, and then we can convert, I guess we can convert the characters into integer so that we can check how many instances they occurred. Wait, so do we need to? No, we don't need to check how many times they occurred. We just need to check what what the unique instances of each characters are inside S, so that it can be converted to T, or vice versa. Yeah, so we can definitely have a Boolean array or a Boolean hash map, which is 26 indexed. And then basically for every 26 iterations, we can replace the characters where they exist. So what is the time and space complexity for the other way around? So the worst case time complexity for the other way around is still O(n), because, oh wait, no, it's still O(n) because we still need to check over all of the elements inside the array and add them and update the hash map, right? And then after updating the hash map, we'd still need to go through the hash map, which is constant time, so it's not a big deal, and replace all of them, right? So it's still O(n) time, and it's still the same space, it's just the other way around, so it doesn't matter much. I prefer the first method simply because I came up with it before. Let's see if there is any other unique solution. So this is definitely a greedy algorithm because we're replacing all the elements and we know that we're making progress. I don't think there's a divide and conquer dynamic approach to this. So, and I don't think brute force is any better. So that's how we can prevent repetitions and avoid replacing a replaced character. Okay, so let's start coding. Okay, so hash map integer, wait, character, Boolean, I guess. Let's see if the code runs. I mean, I just want to check the syntaxes. Yeah, let's check the hash map syntax. Seems alright. I am using Boolean, I don't get it. Where exactly? Oh, Jesus Christ. How about now? There you go. I did remember. It's just a stupid silly mistake. Okay, anyways. For wait. I'm not sure if the question is case sensitive. This is something I would ask the interviewer. Let's just assume they're not egg add. Are they case sensitive? Okay, only time will tell, I guess. Is replace add I false? Okay, it's add for hash set, push put for hash map. My bad. Okay. Just to check things. Cool. It's probably working. Okay. Anyways, that's enough. We still have a constant time algorithm, no growth. Next up, we have a hash map. So what we want to do is now int I is equal to 0, I is less than s.length, I plus plus. no changes if it's the same. But actually, so if we do, no, this is not right, because if we do this, we might change the things that we skipped over before. So we want to change as we go and see if we encountered a problem later on, so that we can return false or true, right? So yeah, because if we skip over a character and then replace it, we might be messing something up from before. So we don't want to skip anything. We want to replace and keep going. If it has not been replaced, and if it has been replaced, we just continue until we get something. Like, so we're replacing as per the constraints given to us, and then based on that, we are checking rather than working to make S into C, rather than trying to force S into C. We're checking if the converted value based on the constraints is actually T. So if okay, so if S dot char at I, so if the character currently at the first string has not been replaced, then in the same key, convert it to true. And then replace character at the specify indice to the corresponding indice at T. I think that's it. So we started off with a hash map. We're checking for every single character if it has been replaced. If it has not been replaced, only then we replace all of the instances in S with from char at I to the instances in char at T. And then if we encounter the same character at some point in S, then we don't loop over this again, because then it will be true. And then if string comparison, string compare. Oh yeah, there's also case sensitivity. We need to do something about that. Okay, so yeah, return s dot equals t. Okay, so if it is equal, we return true. If it is not, we return false. Now, case sensitivity. So regardless of what the case is in S and regardless of what the case is in T, okay, so the problem is with the hash map. Yeah, regarding the strings, regardless of what the case is in S and regardless of what the case is in T, they will always be subsequently, they will be replaced. I'm assuming that they have case sensitivity here. So if one is a capital and the other is small, they will not get, they will not be the same. They'll be, it has to return false, which is why I'm using equals. And if it is still not case sensitive, it will return false. Also, when we are replacing for every character in the hash map, every time we replace it with t, regardless of the case. So that will also check for authentic replacement. The only problem is we only have 26 letters lowercase in the hash map, so we also want to check for other cases. So what we need to do is char at case sensitivity, char at ignore case. Yeah, character dot to lowercase. Yeah, there you go. Found it. Oh, okay, so if we don't want to make it case sensitive, actually, I don't think we should ignore case. I think we also should, since we want to make it case sensitive, we also want to add all the capital letters. So, assuming that it's case sensitive, we have a hash map for all the small letters and the capital letters. Also for all the numbers. Jesus, can the string have numbers? Damn. They did not tell us that. Okay, here's the thing. If they have numbers, they're going to be between 1 to 9, right? So char 0, 9. Cool. All right, there you go. Our regex function. Okay, I just realized that we can have a lot more. Actually, we can have like A to Z, 0 to 9. We can have all those special characters inside the string that we might also need to compare. And as we compare all of them, we don't want to compare in a case insensitive way. We want to compare in a case sensitive way. So let's establish a common ground. Instead of just adding A to Z, let's add all of the ASCII characters from 0 to 127. So that means we'll need to change our hash map. Yeah. No, wait. So I just realized I can just easily create a hash set, and since a hash set returns a Boolean value for whether an element has been added, that should be good enough for us. So instead, let's just have a hash set is replaced new hash set integer. There. Okay. We don't need this. That saves us some time complexity. And it doesn't even need to be an integer. It can be a character too. Jesus. Can you believe this? I was just making things so hard for myself. Okay, cool. I don't know why I was converting it into an integer for hash map. I mean, I guess I was hardwired into an idea and I was just working on it. Now, we can use a hash set. We can have a character data type, and we can just add the characters starting from I all the way to s.length. If it is true, that means we added it. We don't have to do anything else. If it is false, it doesn't iterate. So if it is true, then we just replace all the characters in I inside S with the characters at T. And then we just return s equals T. So this is clearly in time complexity. And after we check whether it has been replaced, we can always, add new characters. And since the characters are directly being replaced and added to the hash set, it's also case sensitive. So I feel like it should work. Let's see. Let's see. Whoa, it's not being replaced for some reason. That is weird. Are we not? So this function here is not working for some reason. That is strange. Why isn't it working? Let's see, string replace. Returns a new string. We have to store it. Jesus Christ. Okay. We must store it. How about now? There you go. Okay, let's try this. AB, AA. We're trying to replace AB with AA. So okay. Okay, so the mapping needs to work on the other way around too. So I guess since we replaced A with A at the very beginning, we cannot replace this different character at S with the same character that we used before, which means that we also need to check if we have added all the characters, because the characters that we've added from, we also can't use them for the replacement either. Okay. So let's say we add A, right? So A is there, so we're trying to replace A. Wait, do we add everything from T or everything from A? Let's see. Yeah, I think the mapping works both ways. So I think what they mean, let's go back to the description. No two characters may map to the same character, but a character may map to itself. So A can be mapped to A, but no two characters may map to the same character. So E must be mapped to A. E cannot be mapped to D. A cannot be mapped to G. So that means, yeah, we have to put in both. And even if one of them succeeds, we proceed with the loop. So let's say we added A, B, and AA. So since one of them is true, we'll still proceed with the loop. So for the next one, do we want to have two hash sets? S. Yeah, we might want to have two hash sets. T. So what we're doing here is, since the mapping needs to be true both ways and unique both ways, we need to add all the characters from S onto S, and we also need to check whether all the characters from T has been added to T. What this does is we can add A both times for every iteration, but we cannot add A again. So if we add, but what does this mean? So if we add B to S and A to T, one of them fails. But if we add B to S and let's say C to T, then they succeed, right? So if we're doing the opposite, C to S and B to T, that should succeed too, and it does because it's completely different mapping. But the only mapping where the same character is being mapped to itself, so they're succeeded. Two different characters being mapped to each other, they're not succeeding because B is being mapped to A, which means that we cannot repeat B for anything else. We cannot repeat A on T for anything else, but we can map A to B as long as A is in S and B is in T, because previously we only did B to A where B was in S and A was in T. So that's allowed, but we don't allow A to B in S to be mapped again, or A to be mapped in T again. So that's how we constrain that using two hash sets. So I'm thinking, and they both need to be working at the same time. And that also works out for this problem domain because two characters can be mapped to itself. However, they cannot be mapped again. So it works out perfectly. And with that, we equal it again. So let's try to submit and see if it works. Jesus, okay. Yeah, this is weird. Based on our logic, it's supposed to work. See what's going wrong. Whoa. That's weird. So replace s.char at I. That is super weird. Okay, let's try to comment this out. What are these? I never tried these. Control plus slash. That's nice. Oh, that's cool. Okay, anyways. Okay. So replace all instances of A with all instances of B. Should be pretty straightforward. I don't know why it's not printing properly. Huh, that is weird. Oh, okay. Okay, that is difficult. I guess the way to mitigate this would be to add them to a completely new character array. So let's try this. Because they have the same length, this helps us. Only if it has already been replaced, we don't do it. If it hasn't, then we'll replace it with the same instance of t, and we do not do anything else. And to avoid further complications as we replace the other characters, we're storing it in a new array. So temp okay, we don't need to start from the beginning because we're already placing every single instance as we start from the beginning, right? So everything before the current position is already done. So we start from where we're at and we keep going towards the end, which means j is less than s dot length and j plus plus. So if it is at the beginning, it's at the beginning, no worries. So we replace temp j char right? So the current character is inside val. Now, if j, and first pass it will always have j because that's where we started. But as we go towards the end, if it is equal to val, then what we do is inside of temp, in the same positions, we put val. Cool. So hopefully I didn't overcomplicate this. We have two assets to check if we are mapping it correctly, and we place it in an entirely new array just to prevent complications as we keep going. That array is completely empty, and it has the same length as S&T. And we use a temporary value to see if the instance that we're currently dealing with repeats all the way until the end of the array. For every repetition from where we're at all the way to the end, we add it to that respective position in temp. Now, finally, what we do we don't repeat the process if it has already been replaced, because that's when the test fails, or if something from T has already been pulled, it also fails then. If it hasn't, we repeat the process. So that proves that every time we repeat the process, it's going to be a new character. So since we're already checking if it's going to be a new character over here, it's never going to be the same character over here. Val will always be updated to something different. And rather than replacing all the way to the end, we just store it in a temporary array manually. Turns out Java's replace thing didn't work out for us. I think that's how they shaped the interviews. So nobody with specific programming language has an edge. And we replace each of those values instances too, so that we don't have to come back. We never do, because the if statement fails on the future iterations. Mm-hmm. String dot value of temp. Yes. Let's try and running this. Oh Okay, there you go. It should work now. All right, let's do this. Two wrong answers. All right, not that great. Memory usage less than 90%, but it's not that fast. Okay, so let's go over the solution one more time. So we have two hash sets. Why we have two hash sets? Because we don't want to replace the same value from S. We don't want to pick the same value from T twice. And those two hash sets check for every possible iteration, including all the special characters and whatnot. And the size only grows, which is why we did so well in space. The size only grows if we add the values, right? And then we come down to a temporary character array. And on that character array, what we do is we put in the values if they are to be replaced. If they're not going to be replaced, we don't put in the values there. But if they are going to be replaced, only then we put in the values all the way from the existing position to the end. And it's okay because we're never going to iterate again for the same character based on the if statement. That's how the entire process works. We try to do it without the character array using the same string s, but what it does is we've seen it just basically on the second runs it might change all of the values inside the string. So the normal Java iteration just does not. The normal Java function for replace string does not work. So yeah, now let's think about how we can make this faster. So we have two hash sets. So I think we need two hash sets anyway, and it has dynamic size, so that we do well on that. I think we do need a temporary character array too, and we don't really use space anywhere else. But the problem is we run through the string, and for every run, we're starting from the string and replacing along the way. And then we move on to the next. We don't obviously iterate the for loop again, if we don't have to, if it's already been replaced. But if it hasn't, then we run it all the way towards the end and check for every instances. So it's amortized. It's not never going to be O(n) squared, but it's like not linear time either. So somewhere in between, I guess, n log n. So I can't think of a better way to come up with the solution. So I guess we're going to look at discussion. 6 lines without maps. Let's see. So take a look at this solution. This solution is definitely better than. Oh wait, no, this one. Wait, which one again? This one, yeah. So this one's definitely better. The idea is they're creating an array of two arrays of 256 size. I don't know why. They could have made it like 128. Oh, whole ASCII. Okay, got it. They could have made it 120, not a big difference. So yeah, so they made two character arrays, and what they did was they just checked the mapping. So they didn't really change any of the strings. They just checked whether one character can be mapped into another. And if at any point we want to map one of the characters into something else completely different using the two arrays at the corresponding indices, and we use the characters to mark the index positions, return false, otherwise we return true. It's a really simple solution. It's great that they came up with a mapping technique and they didn't have to change any of the strings. I guess, yeah, the learning here is that I could have spotted the relationship that all we need to check is basically try and see if all the mapping is successful, because if the mapping is successful, the replacements can happen. So it's basically forward the mapping data and check if the mapping was successful. If it was, return true. If it wasn't, just return false. And that would complete the entire thing in O(n) time. My solution was pretty much O(n) time, except every time you get instances, check for the instances in the remaining strings too again. And even if we don't have the instances in the remaining parts of the string, we still check the remaining string for every new unique instance. And we only don't check it if we have the same instance. which basically increases the runtime. But what we do here is we only add characters to the hash set as many times as necessary and not more. And we have a temp array which is only as long as the character length. But this solution is definitely better if you end up having really long strings. Because here we're having to create another data structure with the entire string set. We're having to create hash sets are better than fixed array sizes, but we're having to create another string set. So if the strings are really long, then we might have even lost in terms of space. So yeah, so I felt hardwired to try and change the string, which I didn't need to, as we've seen. But yeah, both of them work.